Hi, and welcome to this section of the Advanced Algebra Tutor. And in this section, we're going to do something pretty interesting. We're going to learn about transformation of functions. So basically, you already know what a function is. It's just a graph of something that represents what the function's doing. It could look like a parabola or a line or a circle. Well, a circle's not a function, but you know what I mean. Anything that function represents, okay? And in this section, we're going to learn how to perform transformations on the functions. In other words, how do we shift the function up? How do we shift it down? How do we shift it left and right? How do we make it grow bigger and smaller and reflect it and do things like this? So we're going to learn how to use what we know about functions to graph these translations up and down, left and right, stretching and shrinking and so on. So it's kind of a fun a little exercise. There's really not much math as far as actually calculating anything in this section. It's all graphs and pictures. So let's just jump right on into it. Okay, here are some common graphs that you already know, but I'm just going to put them up here for reference to refresh your memory, okay? The graph of a line just looks like this, and I know you know this, but a graph of a line just goes like this, okay? Here's a graph that goes on like this, side to side. It goes on forever in both directions, okay? The graph of a basic quadratic looks like this. And when I say a basic quadratic, something like f of x is equal to x squared. That is going to look like something like, if here's your axis here, okay, that is going to look like, the basic one will look something like this. So it goes on and on forever up like this, and it bottoms out, and that's a basic quadratic, okay? Now, your basic cubic, okay, which would be something like f of x is equal to x cubed, that's why we call it a cubic, basically looks like this. Here's your x and y, and your basic cubic is going to look like this. It's going to go up and over and like this. And we've actually graphed each of these in the previous section, so you kind of know where they come from. This is just sort of a review because we're going to end up shifting and scaling these, and so it's going to be really useful for you to know. Okay, another one is the absolute value, which would be something like f of x is equal to absolute value of x, okay? And that one had a pretty unique shape to its graph, okay? That one kind of looked like a upside down triangle, okay? It goes on forever like this, okay? And the next one I want to talk to you about is a square root, okay? Which would be like f of x is equal to the square root of x, obviously. And if this was your graph like this, then your square root would start here at 0 and it would bend over like this. Okay? The reason it starts at 0 is because if you put negative values in for x, you get imaginary numbers because you can't take the square root of a negative and get a real number back. So your square root starts here and it just bends over. And we did a problem like that before. And the final one I want to talk to you about is a cubic root. Okay? A cubic root. And that one is going to look like this. It's going to look like this. It's going to kind of look like a snaky S, like this, like this. Okay, so, and that would, by the way, be something like f of x is equal to the cube root of x, okay, the cube root of x. So I put these on the board here because I just want you to keep them in your head, and I think I'm probably going to leave them up here, actually, so you can kind of see them. You have your basic line, your basic quadratic or your parabola, your basic cubic, your basic absolute value, your square root, and your cubic root. They all look a little bit different, but they're kind of some of the fundamental functions that you will find in algebra. Notice they're all functions. The vertical line test you do, okay, they only chop these things in one spot, so they're all functions, okay? Now let me write a few things down below here, and we're going to, I think what I'm going to do is leave this half of the board up and work the problems over there because I want to leave some things up here I think you're going to find useful, okay? So the first thing I want to do is to show you something, okay? To shift f of x, so this could be any function, to shift f of x up by c units, So what I'm trying to say here is, if I wanted to take any of these functions, or any function, and I wanted to slide it up c units, or some number of units up, if I just wanted to take this quadratic and shift it up, or this line and shift it up, what would I do? Well, in order to pull that off, the new function, which we're going to call g of x, is going to be equal to the old function, which is one of these on the board, or some other function, plus c. Okay? So when you think about what you have here is, here are your functions. Okay? So you have all of the values of your function, and if you just add a constant amount to it, then every one of these points is just going to be shifted up, and so this is going to be shifted up. Okay? So any function that you have, if you just put a constant, add a constant to it, could be 5, could be 10, could be 2, it's going to shift every point up by that many. Okay? So similarly, now that you understand that, to shift f of x down by c units, okay, to shift it down by c units, what do you think you're going to do? If adding c makes it go up, then subtracting it is probably going to make it go down. F of x minus c. Okay? Exactly right. So if you take any of these functions, or any function that you have, and you subtract off a constant value, then every one of these values here of f of x is going to shift down by that many, and so the whole graph is going to be shifted down. Okay? Now the next two are a little bit more tricky, but I think they'll be clear once I explain it. To shift f of x horizontally, that's what the hor means, horizontally, to the right by c units. Okay, what do? Well, we know we don't just add it or subtract it to the function, because that makes it go up and down. What you do, and I'll explain why here, is the new function that has the shift to the right in it is equal to the old function, but like this. So what you have is, instead of f of x, you have f of x minus c. Okay? Now let me talk a little bit about why that's the case, and then from then on you'll just use this fact all the time. Okay? Let's say you had a function f of x is equal to x squared, which is your famous parabola. You already know what that is. That's a parabola that looks like this. Okay? Now, if I created a new function, f of x is equal to x minus 2 squared, you see I'm doing the shift. I'm shifting it to the right by 2 units, or so I claim. Let's see what it would look like. Now we could obviously plot this. I mean, I could put in values and show you, but just by thinking about it, what you need to know is that this is the graph of x squared, okay? So at the 0 point here, this is the bottom out here, at f of 0, you get 0 squared, and that gives you 0. So this is the 0 point right here. Now over here, okay, if I put 2 into here, x is equal to 2, then the inside of this parentheses is going to go to 0, and f of 0 is going to give you 0. So that's why it shifts it to the right. Okay, this is at 2, okay? Because what it does is, this little notation, when you kind of put it inside the parentheses and put it inside your function like that, it actually kind of resets your 0 point, so to speak. So here, the way to think about it is, at x is equal to 0, that's the center of my function. But now, if I write it like this, x minus 2 squared, I have to put a 2 in here, 2 minus 2 is 0, in order to put the 0 point of the function. So over here at x is equal to 2 is going to be where this new function bottoms out, okay? And that's why it shifts it to the right, okay? So the way I like to think of it is, it shifts it to the right because it's moving the 0 point of that function over to the right. Now if that just doesn't make sense to you, or if that's too complicated to remember, you can certainly just memorize it. If you see something inside of the function like this, and you have a negative sign on it, it shifts it to the right. That's what confuses people a lot at first, is that you wouldn't think that a negative sign would shift it to the right, but in fact it does, because of what I told you there about shifting the 0 point. Okay, so what I'm going to do is I'm going to erase this now. Okay, we're going to do lots of problems with this, so don't worry about it. If you need to see that again, I'm going to have to write it up there again. The final thing I'm going to write is to shift f of x horizontally left by c units. Okay, what do you think it's going to be? Well, it's going to be the new function g of x is going to be equal to f of x plus c. Okay. Once you understand this one just makes sense, because if you go in the opposite direction, you're going to have an opposite sign in here. Okay. So what's going on here when you're shifting left and right, a little bit harder to understand, but it's the same basic thing. You are shifting the 0 point of your function. If I shift it over, I've got to put a different value in for x to make the center of the function 0, and that's why it shifts it to the right. Every point is doing the same thing, and then to the left is just a negative value of c like this. So that was a lot of talking, and I think you'll get the hang of it if we just do some problems. Okay. So what we want to do is we want to sketch the following functions. Okay. We want to sketch f of x is equal to x squared. Okay. We want to sketch that. That's the question. And the answer is, well, we've talked about that all day. That's just a parabola, and we're sketching it so it goes through 0, and that is a parabola, and that is a sketch. Okay. And this is the x, and this is f of x axis there. Okay. Now the next question is, why don't you sketch g of x is equal to x squared minus 3. Okay. Now notice in this case that we're taking our function x squared and we're just subtracting a constant value from it. Okay, so we're basically dragging down all of our values that we had, and we're dragging them down 3 units. Okay, so our parabola is going to look like this. Okay, because for every value we had here, we're just subtracting 3 off of it, and so it drags the whole graph down. Okay, now what if we had h of x is equal to x squared plus 2? Okay, like this. What would that look like? Okay, same kind of thing. We have our graph, we know what the parabola looks like, and for every point we're adding 2 points up. So every point goes up. So you see what's going on here. You subtract off a constant value, drags it down, you add a constant value, it shifts it up. So that's the shifting up and shifting down that we had talked about. Okay? Next problem. Okay, so what if the next problem asked you graph the following? F of x is equal to x minus 3 squared. Okay, so you see it is a quadratic because look, x squared here is the function here, and all we're doing is we're inserting a minus 3 in here, x minus 3 squared there. So it is x squared, it's just that we're modifying the inside there, and so this is going to be a horizontal shift that we talked about. Okay, so this is going to be a horizontal shift. So if this were like this, is it going to shift it left or right? Well, if you look back, it's going to shift it to the right, like this. Okay, and the reason is that if x squared is here, the center of this graph is here for x squared, then it's going to move it to the right here, because if I put x is equal to 3 in here, then this is going to go to 0, and that means it's going to shift that 0 point to the right, because f of 0 gives me 0, and if I put 0 in here, f of x will be 0. So in order to get to this 0 point, I must put a 3 in there. So that's why it tells you that this x minus 3 shifts it to the right. Otherwise, you can just memorize it, that's fine too, but I'm trying to show you logically why that actually works. Okay? Now, what if you wanted to graph h of x is equal to x plus 2 squared? Okay? Then what you would have to do there is look at it in a similar manner. Okay, you have x and f of x. Okay, it's the same thing. You've got x squared going on, but instead of x minus something, you've got an x plus something. So that's a horizontal shift to the left 2 places, and that's going to graph like this. Okay. So I hope this is making sense to you, and basically you can look at it the same way. Look, it's using the function x squared there, and the reason it shifts it to the left is because if I put negative 2 in here for x, which is what I've done, then I get 0 for the middle here, so I'm changing my 0 point and I'm moving it to the left there, and that's why that works. Okay? Next problem. Let's graph f of x is equal to the square root of x. Okay? The square root of x. Well, if we're going to graph that, it's going to look like this. And we talked about this at the beginning of the lesson here. The square root of x just looks like that. Okay? Now, if a little bit later they ask you, okay, now we're going to shift this a little bit. Why don't you graph for me f of x is equal to square root of x minus 3. Square root of x minus 3. How would you graph that? Okay, well, you know you have the square root of x here. You know it's going to look like that because it has the square root of x. That's exactly what you have here. So you know it's going to look like this, but you're subtracting off a constant value for every value of the square root of x you had. So you're basically dragging the whole graph down like this. Okay, so instead of starting at 0, you're starting at -3, and otherwise it looks exactly the same. Okay, so you're dragging it down. Okay, and then finally, if they said, okay, what if we do h of x is equal to square root of x plus 2. Okay, so instead of subtracting a value off, I'm adding a value. Okay, so the graph of that is going to look exactly like this graph, except instead of going down, it's going to go up. So here's positive 2, and it's going to look like this. Okay, so in these cases, all I'm doing is I'm adding a constant value to all of the numbers, and I'm subtracting a constant value to all the numbers. But it looks like the original function. It's just that you're shifting it around. And that's why this is useful, because when you're asked to graph this, you know, you could do a plot of x and f of x, and you can get the values and you can plot them. You know, that takes time. But if you know that it's just the square root of x shifted, then you can very easily draw a quick sketch. Okay, now the next question says graph the following. You have f of x is equal to square root of x. And we just did that one a minute ago, so I'm going to draw it up here for reference. The square root of x looks like this. Okay? And now the question says g of x, go ahead and graph g of x is equal to the square root of x minus 3. Okay? We'll want to graph that one. Okay? Well, we know that it's going to look kind of like square root of x because it sure does look an awful lot like that. But instead of square root of x, it's got this x plus 3. So what you've done is you've modified the center part of the function with this shift. And if you look back in the beginning, it's going to be a shift to the right. Okay? So instead of starting here, it's going to start here. And that's going to be that function. Okay? It's going to shift over to the right. Okay? And the reason it shifts over to the right, once again, is because you're changing that 0 point. Here, at x is equal to 0, you start right here. If I put x equal to 3 in here, 3 minus 3 gives me 0, so I'm effectively starting this function exactly as I had here, but I'm starting it from here, and that's why it's a shift to the right. Okay? Now, if you wanted to do h of x is equal to x square root of x plus 2, okay, then you could graph that, and it's going to look basically similar. I'm doing this mainly for repetition for you. Okay, it's going to look like a square root of x, but it's going to be shifted to the left 2 spots, and the graph is going to look like this. Okay, because if I put -2 in here, this -2 plus 2 gives me 0, and I'm starting my 0 point of my function here. So that basically the starting point starts here instead of here at the origin. So you can see you can use this to your advantage to help you graph things quickly. Okay? Now let's get a little bit more complicated here, and let's say that I wanted to do something really fancy and say g of x is equal to square root of x minus 3 plus 2. Okay? Now this is more complicated than anything I've done before, but you see, now that you know what a shift is to the left and right horizontally and what a shift up and down is, this is just a combination of the two. Because here, we've just done this problem exactly right here. This is a shift to the right. This part, because it's kind of outside of the square root, is just a shift up. Okay? So I'm doing 2 shifts in one function. Okay? So if I were going to do that, I know it's going to shift right 3 spaces and up 2 spaces. That's going to be its new starting point, and it's going to go like this. Okay? I've shifted to the right 3 spaces for exactly the reasons we talked about there. This just adds a constant 2 to the y function, the y value, which is g of x, so it goes up, so you start from here. Okay? And similarly, if you were going to draw or graph h of x is equal to the square root of x plus 2 minus 4, if you were going to graph that, then you could do exactly the same thing. You know it's going to involve square root of x, so it's going to look like square root of x, okay? But this is a combination of a shift to the left with the x minus 2, or the x plus 2, I'm sorry, and a shift down, okay? And this is exactly the same as what we've got here, so you know it shifts left 2 spots, and because of this negative 4 dragging all of the points down here in the y direction, you have 4 here. So that's going to be our starting point, and it's going to just kind of go like this. Okay? So starting with the basic form, you can use your shift knowledge to basically draw that function at different places, and you'll get really good at it after a while. When you see a negative or a positive 4 kind of outside of everything, you know it's going to go up and down, and when you see it wrapped up into the function itself, you know it's going to shift it left and right, and just go on about your business like that. Okay, now up to this point we've done stretching, we've gone horizontal shifting and vertical shifting, and now we're going to talk about reflections about an axis, and we're going to talk about stretching and shrinking the function and making it stretch in different directions and kind of actually stretch out, and also we're going to talk about reflections, okay? So what we want to do is to reflect f of x about the x-axis, okay, then all you need to do is you need to say g of x is equal to negative f of x, okay? And let me show you why that's the case. I'll do that right over here, okay? If you have a function, and here's a parabola up here, and that's f of x, okay? Then if you multiply every point there by negative 1, okay, then this will be negative, and every point you multiply here by negative 1 is going to map it down here. So this will reflect it about the x-axis. That's what you're doing here. You're taking the function f of x and you're multiplying by negative 1. So every value that this gives you, you multiply by negative 1, which puts it immediately down here. And so it's a mirror image down there about the x-axis. That is why that works. Okay? Now, to reflect f of x about the y-axis, okay, then what you do in that case is you say g of x is equal to f of negative x, okay? So to reflect it about the y-axis, you stick the negative inside wrapped up with the variable, okay? And the reason this works is because if you were to take, let's say this was your function over here, f of x, okay? Think about what you'd be doing, okay? If you calculated, if you took the function f of x, okay, and these are the values of x that go in here that make f of x, so here's the values of x, and then here are the values of f of x corresponding to those values, okay? Then by putting a negative in here, what it's saying is that if this were g of x over here, so what this is really saying is that if this were g of x, and if this were the mirror image, which is what I'm claiming it is, and you define it like this, then what's going on here is for every value of x that I put in here, I'm looking at f of negative x. So I'm kind of stealing values from the other side of the grid there. I'm stealing values from the other side from f of x, and I'm making him negative, and I'm flipping him over the y-axis. Because for every value of x that I plug into g, I take the negative of it before evaluating it. So I'm using the same function, I'm still plugging it into f of x, it's just that I'm using the negative value of x. So I'm kind of stealing values from the other side of the graph, and I'm mapping them over here. And that's why you reflect it around the y-axis like this, okay? A couple more things I want to talk to you about. To stretch a graph vertically, okay? All you have to do, this is actually really easy to understand, is you do g of x is equal to c times f of x, where c is greater than 1. All this is saying is that in order to stretch a graph and make it taller, then you look at the values of f of x, and for every value you get, you multiply by a number where that number is greater than 1. So if you were getting values of f of x, you would multiply by 2, let's say, and then that would be your new function. So that function would be that much taller because you're multiplying it by a number. And then to shrink a graph, vertically, it's really the same exact thing. You do g of x is equal to c times f of x, where c is now less than 1. So it's a decimal here. So you're taking the function and you multiply by a value. It's just that this value is now less than 1. Let's say it's 0.5. So I shrink a graph here. Okay. So in this case up here, I may have a function that goes like this, and then when I multiply it, I may multiply that function and make it very tall like this, okay, which is the big one here. And this one right here would be more like if I'm going to have a function, and this was the function right here, and I were multiplying by a value that was less than 1, let's say I'm multiplying by 0.5, then the new value is going to be shrunk. Okay? So stretching and shrinking are exactly the same. You're multiplying every value by a constant. It's just that if the constant is greater than or less than 1 is really what's going on there. Okay? So let's do some problems. Let's graph or sketch the graph of the following. F of x is equal to absolute value of x. Okay? We've already talked about that before several times. So the graph of that function looks like this. Okay? That's pretty much what it looks like. Okay? Because every number you put in here for negative makes it positive. Okay? Now, if I wanted to stretch that thing, okay, or scale it, or do something else, let's say I was going to sketch the graph of f of x is equal to 2 times x minus 3. Okay? Well, the x minus 3 is going to be a shift, and we've talked about that before, and it's a shift to the right 3 spaces, but I'm also multiplying it by 2, so I'm also stretching it. Okay? So what I'm doing then is, if I want to draw my graph here, okay, I am definitely moving my 0 point to the right, okay, because 3 minus 3 is 0, so that's my 0 point. I'm moving it to the right, but I'm also multiplying by 2. So it's going to look the same, but it's going to be much steeper, okay, because for every value of x here, it's going to be that much higher, multiplied by 2, and so it's going to be much, much steeper, and that's why it looks like this, okay? That's why it looks like this. And similarly, if I wanted to do something like sketch h of x is equal to negative 2 absolute value of x minus 3, what would that look like? Well, that one is a shift, again to the right, okay, but it's a little bit different. Let's check this out. It's definitely a shift to the right, so that's my 0 point, and it's definitely going to be steeper, okay, because I'm multiplying by 2, but it is a negative 2. So it's not going to quite look like this, it's going to be negative, and it's going to go down like this. Because remember, to flip a value vertically about the x-axis, you just stick a negative sign on the outside, and so that's what I did here. I stuck a negative sign in front of this, so it's exactly this flipped over, and this is the mirror image of that. Okay? So you see, you can look at this, and you may not ever initially think that, oh, I know how to graph that. You would probably just draw some points and plot it. But by knowing how to shift it and scale it and flip it, you can really do a lot. Okay? Do a couple more quick ones here. Let's say you wanted to plot, or sketch I should say, f of x is equal to x cubed. That's kind of going to be our baseline plot here. Okay? And so you would have is something that looked like this. Right? Something that looked like this. That's what x cubed looks like. And then let's say that you wanted to actually graph g of x is equal to x minus 2 squared plus 1. Okay, a little bit more complicated. X minus 2 squared plus 1. Well, you can... Actually, I want to make this a cube. Okay? So you can see right away that it's going to look like a cubic. It's going to look like this, but it's shifted to the right because I'm moving my 0 point to the right. Okay, and I'm also adding a constant 1 to this whole thing, so I'm going to be moving the whole thing up as well. Okay, so if I were going to plot this, okay, I would say, well, I'm shifting my 0 point to the right, and I'm also shifting it up 1. So this is going to be the new 0 point. Okay, I'm taking this graph, I'm shifting it to the right 2 spaces, I'm shifting it up 1 space. Okay, because this is just adding a constant, and so it's going to look the same. So it's going to look basically like this. Okay, going through a different 0 point there. Okay, and what if I wanted to do something like h of x is equal to negative x cubed? Okay, well, this one looks exactly like this function, except there's a negative sign there, which means that I'm going to reflect it and flip it, okay, over the x-axis. Okay, so what this is going to look like is, it's basically going to look the same, except it's going to be flipped like this. And you can see that this is the mirror image of that. And the reason it's a mirror image is because for every value of f of x, I just take the negative of it. So this one gets multiplied by -1 and moves it down here, and this one by -1 moves it down here. And by doing that, you flip the entire graph over. Okay, so it's the mirror image. Okay. Now, what if I wanted to do f of x is equal to the cube root of x? Okay, that's one of our kind of standard functions that was just really nice to know. So we're going to put it down, and we're going to say that one looks like this. Okay, we've talked about that one. We put that one on the board. It's kind of our baseline function. Okay, and then what if we wanted to start shifting and flipping this one? Let's say we were going to do g of x is equal to negative cube root of x plus 1. Okay, so I've got two things going on here. I've got a shift going on. It's a horizontal shift because I've got x plus 1 inside of the radical, which is inside of my function. It's going to shift it 1 unit that way. But I've also got it multiplied by -1, which is going to flip the whole thing over. Okay, so in order to do that, I'm going to draw this. I'm shifting the whole thing over 1 to the left. Okay, and I'm flipping the entire thing over the x-axis. So what I'm going to do is it's going to look like this. Okay, notice that this is the mirror image, okay, and the whole thing is shifted to the left because my 0 point has moved to the left. If I put -1 in here, I get -1 plus 1 is 0, so that's my 0 point. I've shifted my 0 point and I've flipped the whole thing over. Okay, and then as a final grand finale, last one, let's say I was going to do h of x is equal to 1/2 cube root of x. Okay, 1/2 cube root of x. So here's the cube root of x, okay, and 1/2 of that is basically just being multiplied by that constant there, and now I think you understand that it makes sense. If x cubed looks like this, then by multiplying every single point by 1/2, I'm shrinking this thing, okay, so that means that it's going to look more like this. So instead of being so high, I shrink it down by 2, okay, and that's the answer to that. So this, vertically, this is 1/2 of this right here. So in this section, we've covered a lot, actually, and we've talked about transformation of functions. We have functions, we have certain functions that come up over and over again in algebra, like the quadratic and the cubic and the cube root, and knowing when to shift them left and right and up and down and shrink them and expand them is going to be very helpful in sketching those things, and we've done a lot of examples here. You just have to know what to look for to know when to do those things.